Previous class we discussed about random variable and its different methods to characterize it. Today we will discuss about random process and its different types and how they are characterized. The main difference between random variable and random process is that the sample space, when we are mapping it on the real line, these are numbers. But if it happens that you are mapping head to one waveform cos omega 1t and tail, for example, to another sinusoidal signal represented by cos omega t. That means if you toss a coin, it will be head or tail. In case of random variable, you are mapping head to 1, tail to 0 on the real line. But here you are mapping a head to cos omega 1t and t as cos omega 2t. Means it is also mapping, but mapping from sample space to sum of waveforms. These all waveforms, collection of waveforms. This collection of waveforms is called ensemble, and each function is called sample function. Therefore, a very interesting and the main twist of this concept is that there is no randomness in mapping head to cos omega 1t and tail to cos omega 2t, because in this random process you will always map head to cos omega 2t and t, but the randomness is there in the occurrence of the sample space. That means whether there is head or there is tail. Okay, if it is head or tail, this is the randomness. Therefore, the process associated with is called a random process. A random process can be defined in two ways: by showing the waveforms and also as a sequence of random variables. How? Now you see there have say 4 or 5 waveforms. You are considering a time t1 and the values at that time from each waveform is a random variable. Okay, and as it is a random variable, at any instant the random process is a random variable, and if you take several or a large number of instances, then there will be large number of random variables in the random process. Okay, so what is the random variable in the random process? At any instant of time, the value of the random process is random in nature, and we are denoting it as a variable. That is the concept of random variable in the random process. We can represent by sequence, but here the difficulties in characterizing the random process lie in two cases. How many time instant we are considering, and what is the distance or difference between two instances. Therefore, it is very much difficult to characterize random process. And like the random variable, they are also characterized by joint power spectral density. And first order, it is say px1 power spectral density here at time t2, small px2, and another is joint probability density function. That means what is the joint probability density function of this random variable and at t1 and of this random variable occurring at t2. In the similar way, we can consider for 3 instances. Now, this is the true characterization or complete characterization of random processes, but it is not the gross. For that, we to characterize by probability density function, we must have a prior knowledge of all the waveforms, and that is and how they are occurring in which percentage or in probability, or how it is distributed. In that cases, like the random variable, we go for gross characterization, where we consider the mean value or autocorrelation function, etc. will come in step by step. Now, broadly, we will divide random process into 3 basic types: stationary, wide sense stationary, ergodic, and obviously non-stationary. If it is not stationary, then this is non-stationary, but sometimes there will be some wide sense stationary. Where it will be more clear when we will discuss. In case of stationary random process, we consider that probability density function at this instance, probability density function in this instant are same. That means you are taking the probability density function considering from t equals to 0 with respect to t equals to 0. Now if this origin is changed, whether this probability density function is affected or not is a question. If it is a stationary process, it is irrespective of the shift of the origin. That means probability density function at t1, at t2, at t3, that means random will be same. Another important feature of stationary random process is that joint probability density function of any two random variables or any three random variables of the random process, their joint probability density function does not depend on the time t1, t2, t3, etc. Rather depends on the will always be same. That means probability density function at t1, the joint probability density function of t1, xt2, xt3, xtn we are taking. Now we are taking the joint probability density function of all the n random variables by shifting the total process by capital T, and if this remains same, then we call it as stationary random process. For gross characterization by mean or autocorrelation, what will be the criteria? That mean will be independent of time. That means whenever we are taking the means, wherever it will be independent of time. And another thing is that the autocorrelation function will depend on the time difference. That means if you take the autocorrelation of two time instances or two random variables xt1, xt2, that should depend on the difference between t2 and t1, not on the values or where we are taking t1 and t2. That's all about stationary random process. And for wide sense stationary, now it is clear that it is very much difficult to be ideally stationary. Therefore, for the purpose of analysis, we consider